Hi, hello all. Sorry, it's a LinkedIn page. This is VLSI updates. Hope you all are doing good. And in this session, I just thought of covering a little bit of timing analysis and what are the different concepts are involved in timing analysis and all, as we discussed in the last time also. Okay. Before, I just wanted to go through this page quickly. I found it very useful, and they're covering entirely about what is timing closure and why it is important. They mainly talk about FPG design, but in typical any SOC design, if we take, we are facing a lot of challenges due to the multi-clock domains and the critical paths identification between the logics, so which are really important. And in this session, like, we can just go over this, what knowledge is talking about. Let me just go to the top. This is mainly targeted for APG and written by Phil from Altira, and this talks about what is basic static timing analysis. We all are aware what is basic static timing analysis and why do we need that in any typical design, and different challenges are involved in the timing closer technique due to the frequency of changes. And there are nowadays, the devices are running at very high speed compared to the previous versions or the previous releases in that case. So we have to adapt our design into that, and we have the multiple interfaces like DDR, external memory interface, and all. We have it, so we have to adapt our design, and we have to be like be efficient in designing. That's the important thing here. And because as an RTL design engineer, and it's our responsibility to follow the coding guidelines properly, and to utilize the resources properly and use the proper primitives if you're using any FPGAs, and use that, make sure RTL is inferring the proper FPGA resources to avoid the timing issues and all, because few of the blocks in FPGA is already optimized. Okay, so that is very important. Sorry. And apart from that, we have sorry, my system is a little slow. Yeah, we have a little bit of information on that, and constraint path. We call it as STZ, and generally we call it as XTZ in Xilinx FPGAs, and but both serve the same purpose. The naming convention is little different. Okay, and the clockings, and we know the different terminologies like launching and capturing, okay, latching and the hold and setup time, and arrival time and the required time. So the slack, setup slack and the hold slack, timing exceptions, multi-cycle path, single cycle path, asynchronous path, okay, and a false path, source synchronous, okay, and rise and fall time for the clocks, input delay, output delay for the external interfaces, and there are different analysis like multi corner analysis, and single node corner, slow corner model analysis, and fast corner model analysis, clock uncertainty, jitters, clock latencies. Okay, so in FPG we have different kind of speed grades and IO settings and all, but it's not important for our timing calculations and all. I just going through this because I just want to show the concepts they covered, and what are the different topics are involved in the timing designs. Okay. So timing designs, timing analysis will come after the synthesis part. Okay, in FPG we'll have the front end and the back end part. Front end will do synthesis and all. In the back end part, we will pass the constant as the input, and we have the physical design part and all. Okay, the timing analysis will be done in the back end side basically. And the constraint part, we will have the clock constraints and the input and output delay constraints and all. We will have it. Okay. So let me go to that, the last checklist. What are the checklists we need to do before we ensure the timing closer is perfect. Okay, we can use different techniques like to view the schematic, and to see the connections, and to see the combinational logics in that case, and using the RTS schematic or the synthesis schematic, whichever the stage you want, you can just open it and you can see that, do the analysis on top of that, and we can trace the each and every path of the design using the EDA tools. Okay. So I think here they are giving the setup, rules which we have to ensure that checklist kind of thing. First of all, we need to follow the synchronous design practices. Okay, that's the reason, like, if your designer has a synchronous design, it's very easy for them to segregate and do the constraints, and do the timing analysis. If you have a asynchronous clocking, reset, asynchronous path in your design, then it's a little complicated. And if you have the multi clocks, then you have to identify those, and you have to work with the design team, and you have to identify those. You have to write a constraint, separate constraint for them. Otherwise, the tool will end up in wasting a lot of time in doing the timing analysis for that also, but which cannot be done. But tool will try to do that. So it's important to let the tool know that, like, we have few of the external asynchronous clocks in our design, asynchronous pulse path we have in our design. We have to externally tell to the tool that in order to make sure are going to be fine. And coding guidelines, which is mandatory for any design engineer. And incremental design methodology, which is something no, when you want to do the incremental compilation kind of thing, it will be useful at that time. And yeah, this is important. And the RTL is taking advantage of the dedicated hardware resources. Yes, when you write a code, if you are using FPGA, you should make sure like your RTL is inferring the primitives which are available in the FPGA devices, and which is efficient and optimized in terms of timing and all. We must make sure like we are our RTL is inferring that. Okay, if you want to use the memory, you should make sure RTL is inferring the block RAM, okay, which is the dedicated block in FPGA. If you are using some arithmetic operation, you should make sure like your code is inferring the DSP slices on the FPGA. Okay, complete timing assignments of the design, and multiprocessor features for reduced compilations are enabled. Floor plan timing critical partitions in the design, and perform timing analysis at all process corners. Yeah, okay. Analyze on warnings and errors. Make the necessary changes to remove these warnings and document any exceptions in that case. And document the settings that achieve timing closure. Yeah, it's all about the analysis. Like once your design is done, you can look into the warnings and the different paths which are throwing the warnings and errors or caution. We can do all analysis in each and every corner, and that would be very helpful. But we need to make little bit of analysis on that. Okay. So apart from that, I just wanted to sorry, I just wanted to show. I have some, last time I prepared the path basically. Okay, so the timing parameter wise for the combo path, we know that only the one, we know that there is a propagation delay. Okay, so if you have a more combination and logic here, and it's the propagation delay is going to be more. Okay, so it's our responsibility to make sure the combinational path delay is not bigger than the clock cycle. Okay, so if it is bigger than, then we're going to hit into the issue, or we have to go for multi-cycle path things. Okay, for the sequential circuits, and we have the setup time and the hold time and the clock to Q delay. Okay, so if you see these parameters, but this setup time and the hold time will vary the based on the different standard cells. Okay, so it is important to know each setup time and the hold time of each cells. And yeah, what is setup time? If you see this, this is the flop, and this is my clock which I'm giving it to this flop. And in this clock, I'm just this is my clock edge. Okay, so what happens is like I expect my data to be present sometime before this active clock edge. Okay, so I don't want my data to change in this time interval. Okay, which is going to cause the violate the sampling of data. So this is called setup time here, and once I capture the data, it should be stable for some more time. Okay, so till this period the data should be stable. This is called hold period. Okay, so this is the basic requirement of flop, that any data should be stable before the active edge clock and after the active edge clock for some time, for some interval, and which is defined by the cells. Okay, and there are different timing paths, which is nothing but the input to output paths. When input external input to the output, there will be a combinational logic in the middle, and this is called input to direct output path. Sorry, and there is another path called input to registered path, external input, and we are connecting to the input register here. So in this case only, yeah, we need to write a constraint for all these paths properly, because which is coming from the external device, external source. Okay, so we have to identify the external source and make sure like we are capturing the valid data here. This is called max input delay, max output delay. So we need to use those constraints for that. For register to register path, which is inside the flops, and the path between the flops to flop. Okay, that you need to make sure. And register to output path. This is the register to output path here. Actually, yeah. So basically, if you take the path which takes the clock, this is called clock path, and the path which which carries the data is called data path. Okay, so it should be very clear, like when we do timing analysis, the data path and the clock path should be separate. Okay. Sorry, the data path and the clock path should be separate entirely, so that we can do that calculation, how much time the data is going to take to arrive at this flop, so whether the clock is the clock period is sufficient or not. Okay, so that kind of calculations can be done here. Okay, so to summarize this timing paths, like if you see, there are four different timing paths in any typical design if you take. Okay, one thing is like input to output direct through combinational path, or input to, you'll connect to the register. You need to make sure the data is getting captured properly, so do the timing constraint here. And the register to register, you need to make sure uh, the data is able to transfer within one clock cycle. If it is a multi-clock cycle, we need to define to the tool that the path is multi-cycle. Okay, or how we can optimize this combinational path. And output to register to output path, before you send it to the external device or something, we need to make sure we have that register to uh, output path captured. Okay, yeah, I think this is the basic things I wanted to cover, and going forward we'll have a lot of questions on that. We can have a different few sessions explaining the problems, and how to identify the timing issues, and do the calculations for that and all. So these are the basic things, and this can be done. And uh, beyond that, we'll just try to cover the industry challenges, and what are the different kind of issues are being faced recently. How as a design engineer we can fix that issues, and provide a different kind of solution. That's my primary motto of this session. We will go more into the RTL issues, and how do we fix it through the RTLs, and how do we do the calculations. I think it's a calculation is easy thing, we can do that. We need to understand the real time challenges and all. I will plan for that anyway. So I think for now, yeah, I just wanted to explain these things. I think I explained it. So let us stay connected. I'll come back with the more informations. Thank you all. Bye. Have a good day. Yeah.